In this video, we're going to look at tangent lines and finding the equations of tangent lines and other things related to tangent lines. So the first thing to do is define what a tangent line is. So a line is tangent to a function at a given point if it just grazes the graph of the function at that point. So if we have the graph of f at x equals x squared minus 3x minus 1, and we look at the point where x equals a, then the tangent line to the graph to the function x squared minus 3x minus 1 at that point looks like this. So it's a point that just grazes, a line that just grazes the curve at this point. So it just barely touches it. And because it's a line, it has the equation y equals mx plus b. Now the slope of that line, the m, is the value of the derivative of the function at that point. So the m value is actually equal to the value of the derivative calculated at x equals a. So if we want to find the slope of a tangent line, all we need to do is find the derivative and then calculate it out at that point. So at, in this case, x equals a. So we'll look at some examples of doing that, then finding the equation, and then some other things related to tangent lines. So in our first example, we're going to find the equation of the tangent line to f at x equals x squared minus 3x minus 1 at the point 2, negative 3. So looking at the graph of x squared minus 3x minus 1, we're looking for the tangent line where x equals 2, so x is equal to 2 around here. So if we drop a line down, we're looking for the tangent line at that point. So the tangent line, again, is a line that just grazes the curve at that point. So it's going to look something like that. So we're looking for the equation of that line. We are looking for the y equals mx plus b for that tangent line. So to start, we'll find the slope, because once we find the slope, we can find the y-intercept. And to find the slope, well, the slope is going to be equal to the value of the derivative of our function at that point 2, negative 3. So at x equals 2, because our function is a function of x, so our derivative will be a function of x. So to find that, we first need to find our derivative. So the derivative is going to be 2x minus 3. And now we can calculate that out at x equals 2. So we get the value of the derivative at our point on the curve. So substituting in 2 for x, we get 2 times 2 minus 3, which will give us a value of 1. So that tells us the slope of our tangent line is 1. So now we have the slope of the tangent line, and we also have that it passes through this point, 2, negative 3. So we have the slope of the tangent line, and we have that it passes through the point 2, negative 3. So what that means is if we look at the y equals mx plus b, we now have y equals 1 times x plus b. So really we have y equals x plus b. And now what we can do is we can say, okay, well, if it passes through this point 2, negative 3, then this equation y equals x plus b has to be true for x equals 2 and y equals negative 3. So we can substitute in our x and y value from our point that we're passing through. So y equals negative 3, x equals 2 plus b. And if we rearrange this, subtracting the 2 from both sides, we get b is equal to 5. So now we can say that therefore the tangent line is y equals x minus 5 at that point. So that's at the point 2, negative 3. So if we found it at any other point on the curve, it would be likely a different equation. So this is the equation of the tangent line to that curve at that particular point. And again, it's a straight line. That's why it's a y equals mx plus b. So y equals x minus 5, slope of 1, y-intercept of negative 5. So looking at another one, now we want to find the equation of the tangent line to y equals 21x minus 4x squared minus x cubed at x equals negative 4. So this is a bit different because now we're not being given a point. In the last one we were given a point, we were given an x and y coordinate, Now we're just being given the x-coordinate. So we'll have to take that into account. It's going to add an extra step because we'll need to find that y-coordinate. So this is what the curve looks like. We have 21x minus 4x squared minus x cubed, and we're looking for the tangent line at x equals 4. So kind of dropping down. Our tangent line is going to be at this point, and again, it's going to be a line that just grazes the curve at that point. So it's going to look something like this. It's going to cross it again here over by x equals 3, and that's okay. What we're focused on is this point right here that is just kind of grazing the curve at that point. So we know the x value at that point. We know it's x equals -4. What we need also is the y value. So we can find the y value just by saying, well, this is the curve, 21x minus 4x squared minus x cubed. So if we want to find the y value, all we have to do is substitute in -4 for x. So we'll have 21 times -4 minus 4 times -4 squared minus -4 cubed. And if we calculate this out, we'll have 21 times -4 minus 4 times, don't forget to square the negative, so -4 squared minus -4 cubed. So we end up with -84. So that means this is the point, -4, -84. Okay, so now we have the point on the curve. Next we want to find the equation of the tangent line, the y equals mx plus b. So we can start by finding the m. The m is going to be the value of the derivative at our x value of -4. So we need to find the derivative. Derivative is going to be 21 minus 8x minus 3x squared. Substituting in -4 for x, we'll have 21 minus 8 times -4 minus 3 times -4 squared. So now if we calculate this out, we should expect a positive number because we can see that the line is sloping upwards. So it should be a positive when we calculate this out. And in fact, we get that y prime at -4 is equal to 5. So that tells us that the slope of this line, the tangent line, is 5. So now we have the slope is 5, and we have the point -4, -84. So now what we can do is we can look at our y equals mx plus b, and we can say, okay, well, we now know that m is equal to 5, so we have 5 times x plus b, and now we can substitute in our point, -4, -84, to calculate out our b. So we'll have -84 equals 5 times -4 plus b. And if we move the 5 times -4 over to the other side, so it's going to be -20, but we'll add it to the other side, we'll end up with -64. So that means the equation of our tangent line is y equals 5x minus 64. So that's the equation of the tangent line to this curve, y equals 21x minus 4x squared minus x cubed at x equals -4. So you can see my sketch is a bit off. I had it sloped up a bit too much because it should have been hitting around -64, so probably around down here. In example number 3, we want to find the x-coordinates where the tangent to y equals x to the 4 plus x cubed minus x squared minus x has a slope of 0. So we're not looking for the equation of a tangent line. What we are looking for is where the tangent line would have a slope of 0. So we want to find out where on this curve the tangent line would have a slope of 0. So if the tangent line has a slope of 0, that would mean that m is equal to 0. And if m is equal to 0, that means what we are looking for are points where the derivative because the derivative represents the slope of the tangent line is equal to 0. So we're looking for points, the x-coordinates, where the tangent line has a slope of 0, which means we're looking for points on this curve where the derivative is equal to 0. So we can start out by saying, okay, well, this is our function. If we want to find where the derivative is equal to 0, we'll need to find the derivative. So if f at x is x to the 4 plus x cubed minus x squared minus x, taking the derivative, we get 4x cubed plus 3x squared minus 2x minus 1. So that's our derivative. What we want to do now is find where that derivative is equal to 0. So we want to find out where this 4x cubed plus 3x squared minus 2x minus 1 is equal to 0. So this is a cubic equation. So what I would recommend is using the cubic equation solver mode on your calculator. So using the cubic equation solver mode with an a value of 4, a b value of 3, a c value of -2, and a d value of -1, we end up with 3 values, 3 solutions. We get x is equal to approximately -1, -0.390, and 0.640. So if we now look at the graph and look at those points, we have x equals -1, so right here. X equals -0.390, so about right here. And x equals 0.640, so about right here. And in fact, I know it's at these points because if we think about what a tangent line with a slope of 0 would look like, it would be a horizontal line. So the tangent line at these 3 points would be 0. They'd be horizontal lines. And something to also notice is that these 3 points also happen to be local high points and low points on the curve. So there are places where it's gone down and then it's going back up, or up then down, or down then up. So these are local maximums and minimums. And that's something that will be important to us, finding these maximums and minimums. And we can say that at these points, the derivative is equal to 0. So we have those horizontal tangent lines, and at those horizontal tangent lines we have a derivative of 0, and also that means that they are local maximums and minimums. So again, we were looking for where the slope of the tangent line was 0, so we just found the derivative, set it equal to 0, solved, and got our 3 values. So now let's say we want to find the points on the curve y equals x over x plus 1 where the tangent line is parallel to y equals 4x plus 5. So this is the graph of y equals x over x plus 1. And y equals 4x plus 5 looks like this. So what we want to do is we want to find the points on y equals x over x plus 1 where the tangent line would be parallel to this line. So lines are parallel when their slopes are equal. So what we want to do is we want to find where the tangent line would have a slope equal to the slope of this line. So the y equals 4x plus 5, it has a slope of 4. So what we want to do is we want to find where the tangent line to x over x plus 1 would also have a slope of 4. So what we want to do is we want to find out where does y prime equal 4. So we want to solve this equation. So we want to find out what x values will make y prime equal to 4. So to find that, well, first thing we need to do is find the derivative. Now we have x over x plus 1. So because we have a function of x over a function of x, we'll have to use the quotient rule. So quotient rule says that it's the derivative of the top, derivative of x is 1, times the bottom, minus the top, x, times the derivative of the bottom, which is also 1, all over the bottom squared, so all over x plus 1 squared. So if we simplify this, we'll have 1 times x plus 1, that's x plus 1, minus x over x plus 1 squared, which further simplifies to just 1 over x plus 1 squared. So this is our derivative. We now want to find out where this is equal to 4, so that we have a line that is parallel, a tangent line that is parallel. So we want to now say, instead of equaling 0 like we did in the last one, we now want to find where this is equal to 4. So that means we need to solve this equation. So we have 4 equals 1 over x plus 1 squared. So moving up here to solve the equation, we want to get the x out of the denominator. So I would multiply both sides by x plus 1 squared to give us 4 times x plus 1 squared equals 1. And then I'm going to get rid of that 4. I'm going to say that this is, so dividing both sides by 4, this is x plus 1 quantity squared equal to 1 over 4. And the reason I'm doing that is because now I can take the square root of both sides. So if I take the square root of both sides, I'm going to get x plus 1 equals the square root of 1 over 4. Now, I took this square root of a squared term, the x plus 1 squared, so that means we need to also introduce a plus or minus. So because we took the square root of the x plus 1 squared, we have to introduce a plus or minus. Then moving the 1 over, we'd get x equals, I'm going to put it out in front of the plus or minus, negative 1, plus or minus the square root of 1 over 4. So that means we have 2 points where the tangent line would be parallel to our y equals 4x plus 5. And those 2 points would be x1, negative 1, minus the square root of 1 over 4. So the square root of 1 over 4 is 1/2. So we'd have negative 1 minus 1/2, so negative 1.5. So that would be our first one. And then the second one would be where we add the square root of 1 over 4. And that means we'd have negative 1 plus 1/2, so negative 0.5. So if we look at our graph, at our two x values, negative 1.5 and negative 0.5, the negative 0.5 would be about right here. So if we drew the tangent line here, we would see that it would be parallel. And at negative 1.5, negative 1.5 would be about here. So again, if we drew the tangent line, we would also find that it would be parallel to our y equals 4x plus 5. So again, if we want to find where the tangent line would be parallel, we would find where the derivative is equal to the slope of the line we're looking to be parallel to. So in this case, the 4x plus 5. So we want to know where the slope of our function was equal to 4. In example number 5, we want to find the equation of the tangent line to the relationship x times y squared equals 8 minus 3x at the point 0.7, 2.90. So we're going back to finding the equation of the tangent line, but the biggest difference now is that we are looking at an implicitly defined relationship between x and y. So the graph for xy squared equals 8 minus 3x looks like this. And we want to find the tangent line, the equation of the tangent line at the point 0.7, 2.90. And you can see that it's important that the y-coordinate is specified because there are 2 points on here where x equals 0.7, one on the upper part and one on the lower part. Okay, so to find the equation of the tangent line, we need to find the derivative. We need to find the value of the derivative at 0.7. So to find the value of the derivative at 0.7, so our slope will equal dy by dx calculated out at x equals 0.7. So the dy dx with the line afterwards is saying that we want to calculate it out, and the x equals 0.7 is that we want to calculate it out at x equals 0.7, but we also want to calculate it out at y equals 2.90. So it's important that we specify both the x and y coordinate. So we want to calculate out the dy dx, the derivative, at that point, and we'll probably need both the x and y coordinate. Could be that we just need the x, could be that we just need the y. but likely we'll need both because there are 2 points on here where x equals 0.7. There's only one point where y is equal to 2.90. So let's go ahead and find the derivative of this. We'll have to use implicit differentiation. So we'll take the derivative of the left side and the right side. So when we're taking the derivative of the left side, because we have x times y squared, we are treating y as a function of x. That means we will need to use the product rule when we're taking the derivative of the left side. So again, the product rule says that it's going to be the derivative of the first, so the derivative of x, which is 1, times the second, y squared, plus the first, x, times the derivative of the second, so times the derivative of y squared, which is 2y, times, because we're differentiating with respect to x and we're taking the derivative of a different variable, we have to have times dy dx. So derivative of the left side is derivative of the first, 1 times the second, y squared, plus the first, x, times derivative of the second, y squared, which is 2y, times dy dx. And that's going to equal the derivative of the right side. Derivative of 8 minus 3x is negative 3. So we have dy dx in one place. Now we want to rearrange to solve for dy dx. So cleaning this up a bit, we have y squared plus 2xy times dy dx is equal to negative 3. And we want to get the dy dx on its own, so I'm going to subtract the y squared from both sides. So we'll have negative 3 minus y squared, and then divide both sides by the 2xy. So we'll have negative 3 minus y squared all over 2xy. So now what we want to do is we want to calculate out the valued derivative at our point, at the point 0.7, 2.90. So we want to calculate this out at x equals 0.7 and y equals 2.90. So all we're doing now, and you can see that the derivative depends on both x and y, so all we're doing now is just substituting in our x and y value to the derivative. So we'll have negative 3 minus 2.90 squared over 2 times x 0.7 times y 2.90. And if we calculate that out, so negative 3 minus 2.9 squared over 2 times 0.7 times 2.9, we end up with negative 2.81 approximately. And that is going to represent the slope of the tangent line at our point. So now that we have the slope of the tangent line and we have a point, we can go ahead and find the equation of our tangent line. So we can go to now finding y equals mx plus b. So we have the m now. We have that it's equal to negative 2.81. What we need is the b. And again, we find that by substituting in our point 0.7, 2.90 in for x and y. So if we substitute those in, we'll have 2.90 equals negative 2.81 times x 0.7 plus b. So then if we move the negative 2.81 plus 7 to the other side, so add it to both sides, we'll have 2.90 plus 0.7 times 2.81, which will give us a value of approximately 4.87. So that is our y-intercept. That tells us that the equation of the tangent line to our curve at the point 0.7, 2.90 is given by y equals approximately negative 2.81x plus 4.87. So that's the equation of the tangent line to this implicitly defined relationship at the point 0.7, 2.90. So if we sketch that, just an approximation, 0.7, if this is 2, then this would be 1, so 0.7, 2.90 would probably be about there. So the tangent line would look something like this. So it's crossing again, it's crossing around x equals 2, but at this point, at that point 0.7, 2.90 is just grazing the curve, and you can see that we have a y-intercept of about 4.87. So that would be the equation of the tangent line at that point.